into this afternoon progress, definitely. Move forward. Welcome everybody to this afternoon's discussion session. I've been given we've been put in charge to chair this discussion session, which is going to be probing quantum gravity with future observations. Let me start to say a few words just to introduce that. When I was a graduate student, basically, you're stealing my chair. That's really stealing the chair from the chairman. So when I was a student, and when we were talking about the testing quantum gravity, testing scale physics, basically you were going to one of your professors, and say, "What about the testing quantum gravity?" They were looking at you like, "You are young," and basically say, "Forget about it." And indeed, it was till not long ago the standard law in some, in some circles it still is. I think that this discussion session, the fact that it's here is telling you that things have changed. Let's see what we can say nowadays. So it's a dense slide, but it's simply, I just want to bring on 2 points. One is that you may want to try to understand, say, how is possible that I can test with experiment that nowadays, in any case, below 10 to the 28 electron volt, how is possible that I can test transcale physics? And I just want to give you an example, one big simple example. Take here a dispersion relation like this. Unfortunately, it's smaller than I was thinking. Can you read it? Otherwise, I can write it here. It's very fast. So take that some UV physics at the Planck scale change the dispersion relation of elementary particles, so that, for example, a photon, the photon is not the right type, an electron propagates with a dispersion relation which is this one. I mean, there is an extra term here that breaks basically Lorentz invariant at high scales. Now you say, okay, but to test this term, if I compare it with this one, which is the relativistic one, I need to have kappa order of the Planck scale. But you see, in astrophysics, you have high energy astrophysics process where there are threshold reactions. For example, gamma-gamma that goes in plus minus. These are crucial reactions also for our observation nowadays. So what is happening? What the mechanism is that you don't have to compare this and this, but you have a mass scale in the problem. So when you have a threshold mechanism, gamma-gamma that goes in plus minus, of course, the threshold is set by the mass of the electron. So, or imagine another mechanism given at higher energy, given that this is a very suppressed, Planck scale square, suppress the relation. Imagine we take protons. If you take a proton, the order of magnitude of the momenta of the particle that you need is square root of the mass of the proton times the Planck mass. The mass of the proton is 10 to the 9 electron volt. The Planck mass is 10 to the 28. What you get 10 to the 37 square root, your order of 10 to, let's say, 18. 10 to the, basically, you get the typical energy of ultra energy cosmic rays. So if you probe ultra energy cosmic rays that arrive up to 10 to the 20, 10 to the 21 energy scales, then you're in business to cast a constraint of order 1 at least on this coefficient. Now, given that you have put the Planck suppression outside, this you expect naturally to be of order 1. If you get constraints stronger than order 1, you are in business to say, okay, whatever is doing quantum gravity, it shouldn't produce this kind of dispersion relation. If you ask me, nowadays we are in a situation where if here you put a cube and you suppress only by the Planck mass, we have now constraints, in effective in theory, in modification of the standard model, which are very strong. Unfortunately, our uncertainty on the cosmic ultra energy cosmic ray physics, let's say that at this order business is not so clear. Even worse if you go for neutrino. So I wouldn't say that the field is closed. So let me spend another word about, just to grasp how it's possible that people have started to do quantum gravity phenomenology. Basically, the idea of quantum gravity phenomenology, you don't know quantum gravity, but you explore the possible new physics introduced by quantum gravity. And people in time, at least in my experience, has analyzed several ways to depart from standard model and standard geophysics. One is what I was just telling you about, breakdown of Lorentz invariance, or a deformation, which is something a little bit more complicated that maybe there will be time to discuss later. Or you have a breakdown of translation invariance. So what you're doing, you're saying, okay, space-time is has a fundamental nature which is quantum and discrete, and maybe you break down at some point the Poincare group, and then you can break the Lorentz group, or you can break translation. Translation invariance, for example, was considered in causal set theory, and it brings to diffusion in momentum space, and for example, also that is severely constrained by current astrophysical observation. Another possibility is that if I tell you, well, I give you the Klein-Gordon equation, put a fundamental length scale here. One way is exactly to produce a dispersion relation like this. So how you do that? You introduce another field, you have the possibility to build purely spatial derivatives, and then you can build Lorentz breaking effective field theory. This one, instead, if you want to introduce a scale without breaking Lorentz invariance, another way is that you promote the box to a function of the box. And in that case, for example, you have typical Klein-Gordon equation, which are appearing again in causal set theories in the continuous limit, or in string field theory. There was some set of theories, string field theory, where this f was an exponential box, exponential of e to the minus n squared box, or plus squared. And basically what was happening, you expand the exponential, so you get box, box square, box cube, and so on, with a suitable power of the non-locality scale. Why it's called non-local? Because there are an infinite set of derivatives. This avoids the Ostrogowski theorem that we saw yesterday, so you don't have ghost in this theory. The fundamental operator is the Daran version, so it's everything Lorentz invariant, but it's not equivalent to the standard theory. You can do tests for testing this variation. We have some constraints already from LIC, but the tabletop experiment could do better in the future. Another thing that people have explored is extra dimension. This is probably what you are more familiar with. The possibility that there are microscopic extra dimension or large extra dimension. I just want to cite that also on this, we have done immense progress. Imagine that there are large extra dimension in which only gravity can propagate, but not that this is basically the membrane paradigm. The largest dimension paradigm. What is happening in this case is that if you have a neutron-star merger very far away from you, gravitational waves can leak in the extra dimension, while matter not. So what happens? In matter that if you measure the luminosity distance of the signal, so how much is degraded the luminosity traveling to us, if you have a way to estimate the original luminosity, you estimate the luminosity distance. You expect that the object is fainter in gravitational wave than it is in light. This because part of the gravitational wave will have leaked out in the extra dimension. We have done this thanks to the neutron-star merger observed by LIGO-Virgo collaboration. And we have now a severe constraint on large extra dimension because we measured that the luminosity distance in gravitational waves is roughly the same of the one in electromagnetic waves. So a very exotic idea that there are extra dimensions in which gravity can travel can be constrained now with the current observation. Finally, the last 2 points I want to touch is that gravitational waves have opened also the possibility to probe much more accurately ultra-compact object. And by those, I mean both objects which can be black hole mimickers in the sense that they are not though in an horizon, but they may be much more compact than neutron star, possibly with a light ring, so producing, for example, the shadows that are observed with the Event Horizon Telescope, which should be actually called the Light Ring Telescope. But another thing that you can do, you can look at the quasi-normal modes. And if, for example, you have quantum gravity regularizing the singularity inside black hole, the whole structure of the geometry is slightly different. Of course, there will be some parameter L, say, that is the regularization parameter. If you make it small enough, you will not see anything. But of course, you can cast constraint of how large it could be without affecting your observation. So in a certain sense, high energy astrophysics, gravitational wave astrophysics could play another determinant role. And we have seen today, Francesca talk also about other aspect of this kind of phenomenology that is opening now. Finally, I want to say that this is just, so far we have always looked at the sky for this kind of answer because we are testing gravity, and normally we test gravity with the sky. Of course, there are lab experiments, for example, for deviation from Newton law, in microphysics, but much more can be done in the future regarding the lab experiment. There is a whole branch of research that is moving on in trying to, for example, understand the gravitational field generated by two masses in a quantum superposition. What is happening? So this is not, strictly speaking, what we normally call quantum gravity, are quantum effects of gravity. Is a gravitational quantum physics. And that is another important branch of research that is opening that I would say it is, in all respect, a part of quantum gravity phenomenology. So this I just wanted to present this kind of landscape. And within this landscape, I think we can start to set up a brief list of questions. These, of course, are questions that I put in down and which I encourage everybody to comment on, but as well to propose other questions that they may deem fundamental. So just to be fast, there has been a huge amount of work, for example, in testing Lorentz violation in astrophysics from basically the end of 1999, 1997 till today. But as I was saying, there are missing part of information because both in gravitational waves in different channels, for example, neutrino, these super suppressed violations, which are, by the way, the most interesting one because they're associated to a theory which is CPT even, are not yet well tested. So can we do better on what we have already done? What we can do, for example, to test no locality, which could be another new aspect of physics brought upon us from the relic signature of the quantum gravity regime. What we can test of quantum gravity with tabletop experiment and with gravitational wave experiment as well. And this is a more specific question that was stimulated for some of the discussion. I think that, we are getting to a point in gravitational physics where, in a certain sense, we cannot be content anymore to say, well, there is a singularity, X leones, and forget about it. We know now that the singularity probably are not there. It's just that you need a better theory than GR. And you can very generally argue how the space-time, if it's regular, if somehow you have this regime of quantum gravity that avoid the formation of a singularity, what is going to be basically the geometry that you get on large scale? These bounds, you can think of it. Of course, there is a regime where maybe I cannot describe things with a space-time, but I can kind of extend my geometry over that regime because it's very contained at the Planck density, for example. And then I can produce a solution which is complete. And then you can ask yourself, okay, so is there any chance that I can test this physics? Today, we had partially an answer to this question, but I think it would be very nice to think of the very different ways we can look for this different. I'm not saying that the Big Bang is the only possibility. There could be an emergent universe. I mean, it was just a stub for any kind of regularized Big Bang. And finally, I would like also to put a point that somehow I feel that is not always spelled out completely. While there is all this going on for quantum gravity phenomenology, so you jump forward, you have a leap of faith, and you say, okay, I explore all the possible new physics that reasonably can come up from a non-metric, a completely quantum discrete regime up there. But you can say something different. I mean, when you go below this regime, there must be a mesoscopic range of energy where somehow you do have a continuous spacetime, you do have something that is basically classical. Nonetheless, there may be extra degrees of freedom living associated to gravity. Any theory of gravity, which is a modified classical theory of gravity, generally produces extra degrees of freedom in 4 dimensions. If you go in higher dimension, you have the so-called Lanza-Lovelock theories, which have the same kind of degrees of freedom, but let's forget higher dimension for a moment. What I'm saying is that if we find out that there are variations, there is a new classical theory of gravity, where in some situations, some extra degrees of freedom switch on. So I don't know, you have to go for a theory where maybe you have an addition torsion, you have non-metricity. I mean, there are, the spectrum of modified theory, classical modified theory of gravity is vast. How much we will learn about quantum gravity? Because you see, maybe that you find that there are extra degrees of freedom, but it's not necessarily true that this will make the theory renormalizable. Apart from the fact that we can have also another discussion. If a theory is renormalizable, is it the definitive theory? Or is it simply a theory where you can basically detach your ignorance about the UV by rescaling your constant in a proper way? And because it's not one-to-one. I mean, the standard model is renormalizable, but we don't think that is the definitive theory. No? So I'm just saying that this, to me, is another thing on which myself I don't have a clear answer. So I just posed it to hear your opinion. And with this, I stop. Now I will leave to my colleagues in the panel sometimes to express their opinion. We have something, everybody of them, I see that I organize something, and if they want to add other questions, they feel free, and I shut up. So how we do proceed?
You
decide. So I would go from this.
I thought you were pointing at
it. Let's interrogate first.
Since he has the pleasure to be the only man in the panel, probably you give him.
But he must be chevalier, no? Or you want to have the word before of
I'm more a diplomat, you decide.
Power. I was going this way, but if you prefer...
You decide.
No, then I decide this way.
Okay, I didn't prepare a full speech. I just noted your questions and thought about some comments on them. Yeah, so I think the first question that we should all ask ourselves, that connects to several of your observations, is what does it mean to test quantum gravity? So quantum gravity technology is about testing quantum gravity. What does it mean to test quantum gravity? In the examples you gave, there are different ideas. So in some cases, you are testing, for example, that case, you're looking for a modification of the special relativity. In some other cases, you may look for modifications of quantum field theory. With tabletop experiments, you may look for modifications of quantum mechanics. These may all be related to quantum gravity. Assuming that there is a quantum gravity, all of these theories will have modifications that are not in the full quantum gravity regime, but they are somewhere in between the full quantum gravity regime and their own regime. And the question is how to identify, well, on the one hand, a top-to-bottom approach, start from a theory of quantum gravity and identify what are possible effects. And then you may have a bottom-to-top approach, where you think about what are the possible modifications and you look for them. And if you were to find something, then how do you know that that is due to quantum gravity and not something else? So I think it is important in this kind of research to have clear what are the scales that we are thinking about. So usually, I think you don't have it in the slides. Usually we think about the Planck scale as the scale where we should expect modifications. Even there, well, thinking about the Planck scale could be Planck energy scale, Planck length scales. We could have different physical regimes of quantum gravity where either of the two scales are relevant. So this is also something to keep in mind. Related to this, there is the question related to renormalizability probably. Is there a separation of scales or not? So shall we expect that effects are only visible in the high energy, or is there any mixing between the high energy and the low energy? We have examples of theories, for example, non-commutative field theory, where you have you introduce the high energy scale and then you have effects in the far infrared. So there are all of these, well, these are all questions that I am putting on the table, or points, all points to keep in mind when we are thinking about this. Concerning the tabletop experiments, for example, I think it's very interesting. It's a relatively new thing people are thinking about when thinking about quantum gravity. Well, at the moment, I think we are still at the level of testing gravitational quantum physics, meaning that we do not know how even standard gravitational physics and standard quantum mechanics may interact. We do not know if quantum particles generate a gravitational field that is in superposition of states. So these are all, so for example, this you may say it's not directly quantum gravity, but it is going in the direction of telling you how gravity and quantum physics interact. Still thinking about where could be quantum gravity hiding. So we talked about high energies, small length scales, possibility of mixing, but then should we also search in very high density environments or where gravitational field is very strong? That would be testing yet another area of the full thing. Or maybe shall we go for very large accelerations? That is a bit tricky because it's an acceleration scale, not energy scale. But there are some instances where when you have a very large boost, you get amplification of effects that would be small at small accelerations. You see this especially when you're looking at Lorentz violation, for example. Yeah, so this is concerning framing the question. Then going a bit more, well, related to this, then, so what are the approximations that we should be doing if we want to do a bottom-to-top approach? So we could try effective field theory, even though we might miss a lot by doing that because we put in a lot of assumptions when we do an effective field theory. Otherwise, how else do we implement our deformations? Again, going to what you have in the whiteboard, that is there you're assuming that you have effects that are linear, that are introduced in a analytic way. They are analytic modifications of the physics we know. It's not clear that that is the case. So this is yet another question on the model building side. Then going to what kind of observations could be, or what kind of observations I find promising personally. Well, definitely all the analyses that have been done searching for Lorentz violations, I think they're really interesting. They suffer from a lot of assumptions on the experimental side. So when you look at astrophysical observations, well, this is something I will also discuss in my talk on Thursday. But current constraints that we have that are quite strong, I would say, they imply a lot of assumptions on astrophysics. So when we want to use astrophysics, the problem is that there is a lot that we do not know on astrophysics, and that affects our trust in the constraints that we are putting on quantum gravity effects, for example, on this modified dispersion relation. So for example, in that area, I think at the moment, the most important thing is to understand the astrophysical side rather than the quantum gravity side, because without that, there is not much progress that we can do. Concerning tabletop experiments, I agree. I mean, at the moment, people working on that are reaching, well, they're making progress, like improving sensitivities by a few orders of magnitude every couple of years. So it's really incredible. And at the moment, people are pushing towards increasing the mass of objects that they are capable of keeping in a quantum superposition of states for a long enough time that you can measure. On the other side, they are trying to increase their sensitivity to the gravitational field of smaller and smaller masses. When these two kinds of experiments will improve enough, then it will be possible to measure if the gravitational field sourced by a quantum particle exists in a superposition of states, which I think is really, it would be really amazing to see this. We are not there yet, but by the pace at which experiments are making progress, maybe we will get there soon, or maybe not. Maybe quantum gravity forbids us to reach that regime. So it could be some quantum gravity censorship conjecture in that case. I've been following with a lot of interest recent claims about the discovery of parity violation in the cosmic microwave background, just to throw there another thing. These were claims done by well-established cosmologists, so they're to be taken seriously, at least for the moment. It would be interesting to think about whether this could have anything to do with quantum gravity or with something else related to cosmology, maybe not related to quantum gravity. Well, I think I'll stop here for the moment.
Okay, thank you. I'll try to be quick so that the discussion that can go on. Yeah, I mean, from my point of view, I think that the correct theory of quantum gravity would explain the universe in which we live, which means that it has to be in agreement with whatever observations we have. So that's, I think, and that is an intimate relation between cosmology and quantum gravity, because quantum gravity will allow us to solve some of the problems of cosmology, including dark energy that we discussed, singularity and all that. So indeed, there are two approaches, bottom-up or top-down. And a priori, one would say, I prefer the top-down. But then at the end of the day, you start with top, then you don't know how to proceed. You made some assumption at the end of the day. What you test is not the top, but some kind of intermediate scale that is an assumption. So then I would go more from the bottom up, because that means you know with what you compare and you make these small steps, as we said before. Regarding how you can do experiments and how you can test, I would say that from my point of view, I think that cosmology and therefore gravitational waves could be a very powerful way to test these models. You mentioned about Lorentz violation, and for instance, as far as I know, in many models that you have Lorentz violation, you can find an effect on the scalar perturbations, and that the CMB can give some kind of comparison, which cannot be explained by the generate kind of cosmological parameters. On the other hand, if you take Lorentz violation from gravitational waves, we know that you're going to have Guilia fringes, you're going to have dispersion. In one case, you have parity violation. In the other case, you have waveform that changes, and that will leave a kind of signal in the amplitude. Actually, tomorrow we'll discuss about how the constraints you can put, including what we said about the extra dimensions. So that's a very powerful way of testing the data. Now, I don't have to say anything about the test of non-locality, I'm afraid. About the tabletop experiments, then again, you look for some kind of gravitational effect on macroscopic quantum states. So I'm not sure that at the end of the day, you do a test about quantum gravity. Nevertheless, it's a useful thing to have some kind of idea, but I don't think we're there yet, because as also you said, they need to do much more. I mean, one thing that I know is, for instance, to find from gravitational interaction, superposition of two masses at different location, entanglement, and that could be some kind of figure that you have. But I think yet we're not there, even though a lot of progress is done. Now, in your questions, the questions are lost. Now, in your question, which I wrote down, you have of quantum gravity test in the gravitational wave here, and that is the topic of my talk tomorrow, so I'm not going to summarize it here now. Now, it was this last question that you could put there, whether if we shall find that classical gravity is better than some modified gravity theory, how much we can learn about quantum gravity. I think that's a very good and conservative way of going forward. However, we have to be very careful in the sense that if you find some modified gravity that fits better your data and therefore is a good candidate, we shouldn't stop there, as at least 99.9% of the papers in this field go ahead. You have to make the next step to see where it could come from. If you cannot make this kind of comparison, to my mind, that's out. But unfortunately, there are all these kind of dark energy phenomenological models, which are, and the back of the envelope calculation, they work. It's like Lambda CDM, they were made to work. But then you should see whether it could come. And in that sense, from the kind of models bottom up or top down that exist in the market, for me, for some time, I worked with this kind of commutative geometry, not a field theory approach, and there was a bottom up, and I think it was a nice way. But of course, at some point, you go a bit to the up, and then you have the big kind of gap to bring you to the Planck scale. So there is a lot of work to be done. So I think I would like a bit more time to discuss it. I stop here. Thank
you. Huh?
I'll start where Mairi just left off.
So we have your slide.
Well, just a minute before you present them. If classical gravity is better described by modified gravity, then how much do we learn? I'm not sure about that, because if we have a modified gravity theory, we have some sort of parameter. It reduces to general relativity in a limit. That's certainly true, or else we throw it out the window. And most of what we're doing is constraining our parameter. So do we learn anything about quantum gravity as well? I'm not so sure unless we can identify the quantum gravity theory that this modification comes from. For example, if we found that the modified gravity theory was described by some sort of dilatonic theory, I would automatically think, hang on, this is embedded in string theory. So how can I get what I've just observed from string theory? The answer to that question is, actually, I can't, because I'm not a string theorist. But
you have to kill a lot of fields to go for just dilaton.
But
you freeze them, all of them. You don't want
other things. The thing that I know most about of the list there are tabletop experiments, although I know the tabletop experiments that probe modified gravity theories, and perhaps we can see them.
Should I switch to your slide?
Yeah, why not? Thank you. So
it's not politically correct.
So I have
you can proceed this one.
So I have lab tests. The test that's done a lot of constraining modified gravity theories is atomic interferometer. I think we all know what an interferometer is. And what they've done is really clever. This is actually Holger Muller's experiment in Berkeley. The experiment was suggested by Claire Burridge, Ed Copeland, and Ed Hines. Ed Hines is an experimentalist at Imperial. Claire and Ed are theorists at Nottingham. And there was thinking about testing modified gravity theories with atomic interferometer. Holger Muller saw the paper and adapted his experiment that he already had and published his results. So what he's got is an atomic interferometer with an aluminium sphere. The radius is 95 centimeters, a cesium atom, and you're testing the acceleration of the atom to the sphere. Then, and seeing whether it agrees with GR or there's a modification. Now, it's an atom. So if there's going to be some sort of quantum effect, you might expect to pick it up because we're dealing with an atom. I don't know whether you could compute your favorite quantum gravity theory and see if there's any deviation from in Holger Muller's experiment. But I think that might be one possibility of looking for the anomalous acceleration there. The first experiment, which originally tested GR, was the Etwash experiment. This is Etwash in Washington State. And this one is a torsion balance experiment, looking at the torsion between plate with poles drilled in the thing, and looking if there's any anomalous torsion there. And what it did was put constraints on large extra dimensions, and it puts constraints on parameters of modified gravity. I have no idea if you can use this to constrain a quantum gravity theory or not. I suspect not, to be honest, that Kelly's nodding his head in agreement that you can't.
No, I think you can.
You can, okay. Unfortunately,
Not
this experiment, the Etwash experiment, I don't think is running anymore. I think they closed it down, but it's a simple experiment, torsion balance experiment. One could I think it would be it'd be easier than most experiments to recreate. And if you can test quantum gravity, that might be an easy experiment to see the deviations.
There are other experiments with people we can't talk to anymore. In Dubna, basically, this is all generalized Cavendish.
Yes.
And in Dubna, they're down to the order of 10 microns, which is extraordinary. And those are Casimir experiments with spherical geometry. And I don't know the details of how it works, but they're pretty good at that stuff. So,
Casimir experiment.
Yeah.
so that's quantum at the level of the experiment, but it's, of course, it is measuring, additional components of the gravitational field.
Dynamic Casimir effect?
No, it's come on. That's why I say it's Cavendish, right? It's generalization of what the Etwash experiment. No time dependence, please. That's too much. But
I don't know.
is there a deviation from Newton's law?
I don't know the Dubno experiment. I know other.
By talking to people in Dubna, they told me about it there. You can't talk to them. You can't go there. Talk to them over the internet.
The other experiment would be Casimir.
No, I see. You're into Casimir.
Looking for the quantum fluctuations, and Casimir experiments are getting really accurate now. And being used to see if we can look for deviations from the standard Casimir effect, which would then test gravity. The experiment that, well, to be honest, I have been involved in this sort of parallel plate experiment. I came up with a lovely idea. Oh, it's very simple. You can test modified gravity, have two parallel plates, measure them, pull them apart, measure them again. One you get modified gravity and Casimir dies away as you pull them apart, and you just get modified gravity. The trouble with that idea is that for Casimir, you have to have the plates absolutely parallel. And you can't pull them apart and then keep them parallel. But what you can do is Ricardo Decker's experiment. Here he's got this plate, and he's got things drilled out, and a sphere, and the sphere will take measurements from both the thing where there's the plate and where there's a groove. So the distance is changing. And it's an old, well, I took this from his PRL paper. I think his experiment's still running. And whether something like this, the way that the grooves, I think he's got too many grooves there, and you need fewer, so you can really test the Casimir effect in this type of experiment and see deviations. The trouble with this experiment is that it's theoretically quite difficult to compute. I'm not going to go into the details as to why it's difficult to compute. It's not just the sphere you need, well, it is, because the thing is a sphere and not a plate. And you have to be very careful how you make a prediction from that. So I think that's the end of what I have, yes. The other thing I thought about is whether, that's tabletop experiments. You could adapt all of these tabletop experiments, possibly, to test deviations from gravity. The other thing, obviously, there can be deviations now in the era of accurate gravitational waves, well, fairly accurate. And we've got detectors coming online all the time. And the thing that really blew my mind out was this beautiful image from the Einstein Horizon telescope. I don't have a copy of it, of the shadow of the black hole. I know some people use the shadow to actually test modified gravity. I don't think the test is very accurate at the moment. I don't quite know. I didn't really follow precisely what they did. But any quantum gravity theory has to have something resembling a black hole with a horizon and reproduce this beautiful shadow from M87. That might be obvious. It might be easy to do. I have absolutely no idea. Perhaps a string theorist could do it.
But it's enough you have a light ring. You don't even if you don't have an horizon, you will get, you will get a tiny modification, but if you have the light ring, the main shadow will be there.
You're saying you have a tiny modification.
Yeah, if you don't have an horizon. If you have an object with an horizon, which is not a GR black hole, but still has the light ring, which is depicting the potential normally it's virtually at 3M, you get basically the same shadow.
Oh, yes, but
and you have a lot of astrophysical uncertainties to that, but they have to be taken into account.
You have some
There is a lot of astrophysical uncertainties. So before jumping that is a quantum gravity, I think one should double check the astrophysics behind.
That's the usual
but it's
problem
true,
with
but it's true that if you have a model ultra-compact object, which are inspired by some quantum gravity, which do not have an horizon, then you may have a multiple ring inside. There has been a very interesting work, for example, from Astrid Eichhorn recently on this kind of a class of object. Then you can see, in principle, with new improved observation, not the one we have now, you could see in the future these other rings inside the main shadow. So, but that would be because it's a more radical departure without an horizon, but it's an ultra-compact object with a light ring.
Can you do something like that in the extra solutions to quadratic gravity? The horizonless solutions?
That I don't know. I don't know. I know that you can, I can, describe a metric for an object which is ultra-compact, but I don't know if it would be a solution of quadratic gravity. That I don't know the answer.
Well, we have solutions, but I don't know whether they know how to make
I think Astrid's
shadow.
work is based on essentially regular black hole solutions for the case where you don't have an horizon, and then there are these light rings that can appear inside of the standard shadow. But the metric that they assume is essentially the metric of a regular black hole, I think.
To me, a black hole and horizon are synonymous, so I'm not quite sure what. So if there are other solutions out there.
No, I mean, the metric of a regular black hole, right? You can have 2, 1, or 0 horizons. So of course, you don't have any more a black hole if you have 0 horizons. You have some space-time which is regular, but there's no horizon.
So what is the quantum gravity?
Can I suggest that we have Paulo making this, and then we start the discussion, because here there is a very interesting point here that we can elaborate on. But I would prefer that we close our round and then we move on with the discussion.
Right. So maybe it has been mentioned before here, but let me contribute to the set and list of discussions. When I was contacted, so very recently to join you, I went to the internet and looked for a question, because you sent me a message when I was going to the plane that you were going to look for questions. And there is a very interesting paper, maybe, or in the archive, maybe you know already, and it has been mentioned here. I just want to, sorry. 762, it's okay. I don't know if it has been mentioned here. It's by Renata Law. And the paper is a particularly provocative title called Quantum Gravity in 30 Questions. So on the archive, you can look at it, since look in the internet. So this is just broadening the landscape, not just on the phenomenology, but also the phenomenology, and also with far more questions. The other, which I'll just put here, also you can have a look, and I'm going to mention something for it. It's just let me now be a bit of a pessimist for it. So this is a review that came recently, and it basically says, well, it's harsh times that we are facing. In essence, it takes the CMBR, and then we have the angular map of temperatures, and you can write this in terms of a sum of these well-known objects. And then you have this thing here that you all are aware of, and that I must confess, as more like a theoretician, I don't know so much. You have the L0, the monopole, which is the 2.7 Kelvin. Then you have the dipole, and then you have to larger than 2. You have what can come from the perturbations of density in the very early universe. Well, this review delves with what we can have, say, of quantum gravity corrections to the Schrödinger equation and beyond. And the reason I'm saying of being pessimist is that if you consider just at the level of L equals 2, a variation of the L equals 2 coefficient with the term that has no quantum gravitational corrections, this is to the order of 10 to the minus 6. you are taking a bunch derived from Einstein, Hilbert, the Gaussian wave function for the perturbations on the wave function of the universe, and it's this. Why am I saying that we have grounds to be a bit pessimist? Because when you take the similar calculation for L equals 2, and again, at no corrections at all, this is just the cosmic variance. Let me call it CV, not curriculum vitae, but cosmic variance. And this is of the order of 0.63. So from here to here, it's a huge gap to search for. So, but it can also be positive. So as I've been talking with some people over lunch, so 50 years or 60 years ago, if anyone thought about detecting gravitational waves, people would even say, do you believe in that? Now it's a reality. So maybe we can go up to that direction. But now I'll let it keep it there, because that's final question that you put there gave me soul warming. And if I can just...
Yeah, before you erase that,
Yes.
I don't understand your quantum gravity corrections, how you calculate how they come from. No, because if I want to take these numbers seriously,
Right.
this result, I should know how the calculation was done, was quantum gravity thing, because all the stuff that you write before is completely standard classical.
Absolutely. So let me just,
briefly, because people probably have other questions, but if I want
very briefly, rigorously, and if you want to read it through a long review.
No, I just want to see where the quantum gravity came from and how it was calculated in one word.
So you take the wave, you assume a wave function of the universe, so you have to assume something, and then you expand it in the WKV form in the sense that you have powers of the Planck mass. To one particular order of expansion, you get beyond the Hamilton-Yakov equation on the 3 metric, you get the Schrödinger equation, and at the next order, you get something called quantum gravitational correction to the Schrödinger.
How do you calculate the CLs there? How you do perturbation theory?
Because you solve the quantum gravitational correction to some extent of that Schrödinger equation, it's a bunch of its state, and you have there corrections that you can compute. You can compute them. When you compute them, you get the variation, for example, of this, which is well-known standard result, and you get this. But to be short, these are a bit of pages here. So these are work by, say, Leonardo Chatelier, if I can put it correctly, also Brizuela, and they have done this very elegant. And it's already, I didn't do it, they do it. So this is a review.
I'm saying that because a very delicate story of what you call perturb, what are the variables you are going to perturb and how you do the perturbation theory. So that's a lot. It's a bit. Anyway.
Let's postpone this for the discussion.
I'm planning to be pessimist, but nevertheless, I'm saying it can be computed and it can be discussed. So there is hope, but more hope. And now going to that final question. So let me say, and if I'm short of time, you tell me.
Well, 2 minutes.
2 minutes. Okay, 2 minutes is okay. So I will say, if we shall find, let me get straight to the point. If you find torsion on the cosmic microwave background radiation, if your modified theory is gravity with torsion, I will say yes, like Homer Simpson, Homer Simpson, the character of the... So I will say immediately, okay, you don't have GR, you have supergravity. That's the elegant, logical, consistent, beautiful theory which brings you torsion in a self-elegant way. So bring me torsion in response to that last question, and I will say it's supergravity. Or say superstring, but there is supergravity. Beyond that, I will also pick up comments where people say, maybe you have to challenge quantum theory. And for instance, if now I will not erase, but I will write here, if you find somehow in your tabletop experiment non-commutativity, the quantum deformation of quantum groups, this may require a different way of seeing quantum mechanics or not. Moreover, if now you consider solid state physics, and they have been doing bravest and bravest results and experiments, namely on the wave vector in terms of the frequency in terms of the wave vector. So if some works on the Ising model can be done, this may, for example, assist you to consider fractional calculus. So maybe this is something that is seriously being explored. Of course, so far, nothing. It's true. Just to conclude, and it's that word again. And when people ask, I mentioned here, maybe quantum mechanics has to be treated differently. So it's that question that Einstein put in 1917. How do we do with our ergodicity in a quantum mechanical way? So there is still no proper answer to that question. So only for integrable systems, only for something that come about as a spectroscopy of the Bohr-Sommerfeld, you can have exact solutions. All the rest is approximate. It's a bit like we all been taught about solving the Schrödinger equation for the hydrogen atom. It's an exact solution, either Schrödinger or Dirac level. But now you put not one electron in the proton, you put another electron, you have the helium. So the helium atom is a paradigm for quantum chaos. You cannot have an exact solution for that unless you do some approximation. So probably when you're trying to deal with chaos at the quantum level, and it's something that is not properly defined, you don't obtain something nonlinear from a linear equation. This may force us to deal differently with quantum mechanics and eventually quantum gravity. So maybe this is not at the level of provocation. It is maybe the level of saying something not properly balanced, but I think it's worth it to consider if I shall find that some classical theory is better described, or you have to change quantum mechanics, what does that tell you about quantum gravity? A lot. So let me just summarize, bring me torsion, and I will tell you that's supergravity. I'll go to the streets and I'll start shouting to the masses.
Very good. So let's move on now to the second part of the discussion. So questions from the audience. Okay.
So torsion in other theories, you don't get torsion.
One can get torsion. Yeah. I don't understand the statement.
So
why
yeah, so
there is
It is a wishful.
okay.
I think what they're asking is that why you think that detecting torsion would straightforwardly link you to supergravity?
Not straightforwardly, there are other theories, but it is like a beauty concept of science, like in the Dirac sense. I can only imagine if you find rigorously that torsion is unavoidable consequence of your measurement, and you cannot throw it away. If it's there, no one has seen, okay, but if it's there, for me, it is only the meaning of you can only go forward and you'll find supergravity.
Yes, but for example, my point of view is that in a certain sense, if you think of Einstein-Cartan, to me, it's more an extension of general relativity. It's something you need to consider once you want to complement to discuss the gravitational field of fermions, for example. So to me, it would be still very interesting to detect torsion, but I don't know how that would link to quantum gravity. I mean, it could, but it's not for me a straightforward path.
It's not as beautiful. It's like you have a beautiful painting and you get just a square of it. You like the square of it, but I'm telling you, it's much more than that.
Yeah,
so it's just...
It's a personal view.
Exactly.
It's a question of faith. Okay.
Please.
Maybe let me follow up on this. Are there any chances of actually measuring torsion? And if so, where?
Torsion is start to be much, I mean, okay, we know that torsion. All right, let me try to not say things to boast. Torsion, we have a good evidence that we should not propagate, because if you have torsion waves, you probably would have seen, I mean, you already have a constraint from binary pools, no? So there is a branch of theories of torsion that you can always cook up in such a way that is very stiff and that you don't emit a lot of in torsion waves. So, but for example, Einstein-Cartan theory, you don't propagate torsion. In those theories, there is a very good analysis in a book by Friedrich Hell that he was showing that the density at which you need to get with fermions in order to switch on torsion are very high, are above a neutron star level. So, for example, there is a paper by Trautmann where it shows that at the Big Bang, torsion can regularize singularity because it becomes important before of the Planck density, and it acts in a way that you can always see it as an extra field that violates energy conditions, so can regularize the singularity at the center of a black hole, or it could regularize the Big Bang if it's there. But detecting it is very difficult because I guess that there are, this is, I don't know the real answer, but I think that it would be easier if we could start having this experiment where you see the gravitational field with fermions. Maybe that is the way. And other things I can tell you is that if you look at the Reichenau equation, the equation with which in horizon dissipate perturbation, in some theories of torsion, not all the theories of torsion, even those where you don't propagate torsion, the presence of torsion allows for the horizon to have not just a shear, but also a twist. And that the bonding mass you would see at infinity would be slightly changed. But of course, we don't know a priori how much could be emitted. So that's all I have to say. Robert.
Oh, sorry. I have a question to you. How do these constraints on non-locality work? Can you just a couple of words on?
Well, a couple of words.
Can I say something before? Because mine is a
follow-up.
It's a finger, not a hand.
As long as it's not the middle finger, we're happy.
So I'm a bit puzzled when you said that dynamical torsion is a problem, but the torsion is, after all, can be viewed just as an extra tensor, right? So you have maybe a dynamical independent connection, but then the difference between this connection and the Levi-Civita connection is an extra tensor. Now, depending on how you write, depending on the action you choose, you can give actually any mass to these extra degrees of freedom if there are extra degrees of freedom in the torsion. So
you mean that you make it very short range?
You can make it very short range.
That is what I was saying. You can tune the theory in such a way that you can propagate torsion, but it shouldn't propagate very much. I mean, the problem is that still you want that in the binary pools, we know that the period scale with the load that you expect from the quadrupole. So if you have other energy loss, even if you don't get the wave here, you may still be in trouble. You need to dump to make it very difficult to even stimulate this, not just to make them separate.
What energy scales? Because, for example, I have a model where there is a dynamical torsion, and there is only one scalar extra degree of freedom. And I found that by choosing the action appropriately, this can be the inflaton. But in that case, you have a dynamical torsion.
Have you tested your theory against the binary Pulsar constraint?
Well, this is very high scale.
But I mean, I don't know your theory, so
well,
I think
it is just after all,
no?
if you change the variables, it's just general relativity plus a dynamical scalar with some potential.
And normally, that would be a potential problem with the binary pulsar. It's worth checking. I don't know, even if because you're saying it's a short range the field, but if the problem is the energy balance. If it subtract energy to the orbital of the binary pulsar is still at the reducing the period with a law that is different from the one of pure GR, no? So if you are convinced, test it. I mean, I don't know.
It's just general relativity plus the infraton with some potential.
But that is exactly this test of the binary pulsar. Generally, they are constraining also scalar tensor theories.
Yeah.
It's not that they're ruling out all of them, but it's not a problem of how far they go, how much is long range the interaction. The problem is that if you have emission, too much energy goes in this other wave, it affects the scaling of the period of the binary pulsar, which is very precisely measured, and you have a sensitive, I mean, a deviation of GR. We are talking about a measurement over years, so it's very precise.
But
now we have a
this is really short range.
A short range doesn't mean that it's not emitted. One thing is to say that you have a Yukawa potential. One thing is to say that there is no energy loss in that channel.
So in the kind of extremely small error bar, you can there play and put constraints in your thing.
Yeah, that's probably you should try to check the new quadruple formula in your.
This is really, so there is some difference, but it's mostly similar to Straubinski model. So
there are two pulsars.
There's a potential that looks like this, like many other.
Yeah, but I mean, until you do the calculation, you cannot just say it's given that is similar to Straubinski, because it depends on the actual parameter. And for sure, you can get a constraint at least.
Moreover, I'm pretty sure that you can hook up an action such that the Straubinski scalar can play a role of dynamical torsion, because you can write whatever action you want for this. So depending on the action you write down.
Yeah, but I don't understand exactly how this is related to the discussion. I mean, of course, you can create a problem
this is
dynamical torsion that pass the current constraint.
This is related because
they will tell you about the fundamental theory of nature.
This is related because in the last sentence you write how much we can learn about new physics with modified gravity, and you make the example of metric affine theory. Metric affine theory is at the end, from the observational point of view, can always be reduced to a metric theory, in which the connection is the Levitz-Hillier connection plus some tensors. And you can give whatever action you want to these tensors by choosing the starting action. This I'm pretty sure.
I'm not sure I understand your point. Whatever action you want, I mean, you start with a theory which is a symmetric affine theory. Of course, it's obvious that you can recast it in a metric theory plus extra degrees of freedom encoded in some tensor. That we know is actually one of the problems to work with gravity, that you have all this representation of equivalent theories. The problem is that if it is just a different representation, we'll have the same prediction. So you will have a different set of parameters now to constrain, but the constraint will still be there. Now, giving whatever action, you have observation. So if you make the torsion dynamical, you have to worry about, for example, the binary pulsar constraint. If you don't do, maybe you work for ages for any theory, that then the binary, and you cannot just make an argument, say, you see, is heavy the field. I mean, you have to really look at the constraint, the way it works. I'm just saying that from the point of view of quantum gravity, to me, if we discover that there are extra degrees of freedom in gravity, not just the graviton, that could be informative. But it's true that there is this problem of representation that I find very, this is why I often prefer to talk about degrees of freedom and not of fields. Because degrees of freedom are fundamental. Representation, the encoding of these degrees of freedom in set of fields, as you just said, it's just a matter of representation. I wouldn't give too much physical meaning to the representation. Is the degrees of freedom counting that to me would be very, very interesting. But how much you can make up of the whatever is the substratum theory, the fundamental theory, of course, you may have the point of view, say, who cares? There is no substratum theory. If I find the theory which is renormalizable, I stop here, I have the theory, and that's it. I mean, you may have also this point of view. I'm not.
No, I don't. But really, my comment is about this metric affine theory. So, to me, there's nothing more that, from the observational point of view, that if you make it dynamical, of course, the extra connection, GR plus some tensor, so it can be scalars.
And then you have to use all these.
I think the point is there will be some new scale in that case.
Yeah.
And then you do, I mean, take some experiment that Stefano was mentioning, you will get a constraint on your scale. It should be lower, graded at some lower bound. That's it. I mean,
And you have to check basically.
We did that at some
Yeah.
point with the theory, then we did exactly the factor that you said.
Yeah.
and put constraints.
I mean, you can take
You can give whatever action you want to this extra degrees of freedom.
no, but you always have some.
I mean, it's
There are
whatever
applications
action.
can be used out there.
I mean, it's not whatever action, because if you have a fundamental theory, say you want to start from quadratic gravity, then you must have predictions for these coefficients. and then-
Sorry, I'm not saying this. In a given fundamental, you complete quantum gravity theory, then you have predictions.
Okay.
But what I'm saying is that if you start from a metric affine theory, so at the beginning, the connection is not the Levi-Civita one, but there is an extra tensor.
But there can be more. There can be also non-metricity, not just a torsion.
Well, it's the dynamical connection is you can always write down as Levi-Civita plus a tensor. This is for sure. And
No.
then this extra tensor.
No, the way you say it is not correct. I mean, you have that you can have non-metricity and torsion. What you
But
just
that's
said is
also
true
tensor.
if you have a symmetric connection. If you have a connection, you can split it in a symmetric part and an anti-symmetric part.
This
The
is
anti-symmetric
tensors.
part gives you the torsion.
These
The
are
symmetric
tensors.
part can be Levi-Civita,
Yeah.
or it cannot be Levi-Civita, and then you have a torsion part. Sorry, a non-metricity.
The connection is the Levi-Civita plus a
But still,
tensor.
there are constraints. That's
Yeah,
what
I
we
mean,
say.
No,
if
it
you
should be non-metricity.
Except for tensor.
But even
That's
if,
what
I mean,
I'm
you have
talking
some
about.
parameters, you can combine
There are two
constraints from a
tensors.
different
It's
stuff.
different. They have different symmetry. Non-metricity and torsion are two different.
It's sum of tensors.
Vabbè.
Is a tensor.
Okay, anyway, I think that this is not quantum gravity at all. So let's go back to quantum gravity.
Okay, let's go back to quantum. Yeah, I have a question for the panelists, but first I would like to make a comment. So I think it was said more or less, but I would like to make it more explicit. I think when we talk about quantum gravity, we should, or at least probably quantum gravity, we should distinguish between pure test of nature of quantum gravity, or quantum nature of gravity, and test of quantum gravity approaches. Because usually when we think of quantum gravity approaches, we have in mind some high energy regime that maybe at the moment we cannot really reach. But as we've learned from Stefano, from the speakers, from the panelists, we also have tabletop experiment where we are working on low energy regime. And so we can somehow test nature, quantum nature of gravity in a model independent way, in the sense that the low energy regime there is Einstein gravity, we quantize it, and we try to see whether we can access some quantum nature of this gravitational field or whatever it is. And in, for instance, in the last year, there have been proposal of like gravity-induced entanglement, or like a possibility of detecting even gravitons, so quantum effects of gravitational waves and so on. And so it's good to make this distinction, because in principle we say, I don't know, we have some dispersion relation which violate Lorentz, local Lorentz, whatever. But yes, fine. But I don't even know whether that in principle is a net feature of quantum gravity. For me, a net feature of quantum gravity would be something that is really like h-bar dependent. It would be, I don't know, even at low energy, you can see it in a tabletop experiment. If you want to put it right, but in principle, you can just modify gravity theory, which is purely classical, have some Lorentz violation, for instance. It could be in principle. So I would say that to really say that we have quantum gravity, or that at least gravity is quantum, you can ask this question to energy, and an experiment doesn't care about the approach that will complete gravity at high energy. Okay. So having said that, my question for the panelists is the following: do you agree? I think, from my point of view, the answer is yes, but sometimes people think in different ways. Like, let's suppose one day we observe primordial gravitational waves. Okay. Would you say that that's a test of the quantum nature of gravity or not? It's a question for all the panelists. So once you observe those primordial gravitational waves, would you say, okay, we know that gravity is quantum?
Well, it depends on what you're observing exactly. I mean, what you observe is a classical
Sure.
wave.
But you have a
So
framework
if
in
you-
which
if
you are
you
quantizing
know that they are
fluctuations.
Yeah, but in a
of
calculation
primordial
of
origin,
You are
then
quantizing fluctuation,
You
like
have
a
gravity.
scalar field, you would have some.
yeah, so they came from some quantum, and then there was a transition to classical.
Right. So
And keep in mind that the way this transition happens may have different imprints on the signal you see later.
no, so what is your? Would you say no? We still
Well-
cannot say that gravity is quantum, or
I will give an answer. Definitely not.
Yeah.
Because there are many other sources of primordial gravitational waves. For example, cosmic strings.
I understand that. Let's suppose we know that these are like primordial gravitational waves
I'm talking
How
about
do you make
primordial
this?
gravitational waves.
from
How
some.
can you make the distinction where they come from?
Yeah.
That's the question.
Yeah, because
And
the
there
thing
is
that
not,
they-
there is not a distinct way to know their origin.
Exactly.
Because
So
the thing
that's
is that
the
you observe
question.
something that is classical.
normally when there was the famous B-modes and infamous detection,
Right.
people were saying that it was a proof of the quantization of gravity because they were making, they were thinking of the kind of calculation where you also
People were trying to get the
the
Nobel
metric,
Prize.
and then you say, if you know that those things are coming from that, then at least you have gravitons. To me, by the way, it is like proving that to your phones, which is okay,
Okay, so the answer would
which
be
is
no.
totally okay,
Yeah.
but it's not definitely probing what I would call definitely the discrete
The quantum nature of-
Anyway,
yeah,
that
no.
is an. So there was before. Francesca, and because it's a follow-up, so then after it was a follow-up, yours or a new one?
If
Was a
it
new
is
one.
about primordial gravitational waves, I'm happy to go after, but
Okay, to yours it's not a follow-up because you had a thing.
it's a follow-up on the first part of the comment and the question for them.
Okay, so
But
let's listen. Yours is a follow-up.
That's a follow-up. So there are actually people who are trying to study whether you, given cosmological perturbations, whether you can find out whether they're of quantum origin or not. And one group that's working on that is Jérôme Martin and Vincent Venin. But I don't work on that. So this is just a reference group.
Okay.
Yeah, and I think is that the answer to this it depends strongly on what mechanism you choose
Follow-up
to
or-
do the quantum to classical transition.
Comment.
So it's
Which finger? Oh, then the one for-
How many fingers? Well, not which finger. How many fingers? What?
Let's wait the first, Francesca, you have the follow-up on his.
Yeah, it's a new question, but it's related to the
If
first
it's a new question, there is other people.
It's related to the
Okay.
first thing.
Okay,
So
give
it's a
the
follow-up.
question.
Because so I appreciated a lot your comment on the difference between testing the quantum nature of gravity and testing approaches to quantum gravity. And I had a question to Giulia, but to everybody, because you mentioned at the once when you were talking about entanglement that comes from a gravitational interaction. You were mentioning the possibility of some kind of quantum gravity screening so that we cannot see quantum gravity as low energy. I don't know what you are referring to. So
I don't think I mentioned entanglement.
Nobody said that. The only thing that I said myself is that I didn't say about screening at all. I just said that goes one kind of tabletop experiment that you could have the gravitational interaction between the two masses, which are superposition of location, and that you see it as entanglement. And she didn't say anything about screening.
no, she said quantum gravity censorship.
Well, that was a kind of a joke, but what I
No,
was
but tell me
what I
about
meant
what you
there-
had in mind.
What I
because
had in
don't know
mind there
about
is I was wondering whether we will ever be able to access with tabletop experiments the regime.
So the answer is it depends in 5 or 10 years, but it's probably yes.
No,
But you were making two
because,
different
I mean, you
points.
may have, what I had in mind, for example, is that, and this is something I will mention in my talk also, you may have mechanisms that introduce the coherence due to quantum gravity, for example, that would prevent you to put in a quantum superposition masses above certain value.
So what you have in mind is that the coherence
So,
maybe
so quantum gravity may induce additional decoherence that will prevent you from doing the experiment you want to do.
Do you know about any computations in the, or
I'll show it on Thursday.
Okay.
Okay, so we had a question there, and then
Yeah, so I was just had a first small comment. You mentioned there was evidence from observational data on the parity violation. Like this wasn't it true of a couple of years ago, but recently there was an updated study that this was just an issue with the simulations they were using to do the inference. But at the end, I think now it's not.
How recent?
It's not anymore. There's no.
How recent was this paper?
I don't remember. I think the last year.
Well, I'm not sure. So last time we
had a
had a
meeting
workshop on this in May.
can follow
and
up.
I think we're still,
cosmologists that
very-
were super excited by some recent observation.
We can follow up maybe after.
Yeah, I'd
But
like to see that.
and the main question I had is, do you think that using quantum computers, this is a possible avenue to test or help with quantum gravity, or is this something completely unrelated?
Well, I have no opinion on this.
I have a comment on the first part and a comment on the second part. So the comment on the first part regarding symmetry breaking in cosmology.
It was parity violation.
Yeah, sorry, the parity violation was comes with chirality, basically.
Yeah, there are cases that I see.
They put as a catcher
Very
much
much.
higher than the people.
Exactly. And if you do quantum cosmology, you have the host term with gamma, where gamma is exactly what may give a chiral term. So this is something that can be explored and something we are thinking about and can go exactly in this direction. Second, the answer to your second point, that is how quantum computing can help quantum gravity. So it can help in different ways. One way is that you can use the quantum computer as a quantum simulator for a quantum geometry. So in particular, there are certain quantum computers that indeed use molecules that have exactly the structure of a tetrahedron, like this ones. So you can use them in order to understand the behavior of a geometry. It is a discrete quantum geometry by simulating this directly. Because one of the problems that we have in loop quantum gravity in particular is that we control very well a single quantum space, but we have more difficulties to control all the approximation that comes when we have several quanta. So when you can use the quantum computer in this way as a concrete quantum simulators, and there are a lot of work in this respect. A different thing is when you want to use quantum computers in order to do computations for quantum gravity. So what we have done so far was to put on a quantum computer the transition amplitudes for quantum gravity. People have done this. The result was that so far, of course, as it's always the case with quantum computers, you can actually do less than what you can do with actual computer. But things are a bit changing these days. Because, for instance, in a work that will be published hopefully in a couple of weeks, for instance, we have also studied the behavior of the quantum Hamiltonian constraints acting on a quantum geometry using an algorithm that then can be exported on a quantum computer. So the idea is that what we have done is the first step then to run this on a quantum computer. And we are getting some results numerically that have been not accessible for 20 years in this field. So I think that because of the fact that quantum computing is a field that is growing so fast, we have opportunities to do things there. And in any case, we can always get more money because if our friends get so maybe we can do some good things for
Okay, we had a question there. Thank you.
Well, my question will be rather comment than question about Lorentz symmetry breaking and gravity. Actually, if we want to consider Lorentz symmetry breaking and gravity, we should think by which theory will be the better, because in principle, yes, we have several rather good Lorentz breaking theories in gravity. For example, Chern-Simons modified gravity, Bumblebee gravity, which is perhaps the best because of natural reason to introduce Lorentz symmetry breaking. Einstein letter more studied, but with some disadvantages. But the question, if we introduce Lorentz symmetry breaking, we should nevertheless think about the problem of consistent quantum dynamics, because we should nevertheless think how to solve the problem of renormalizability. Lorentz symmetry breaking itself seems to do not improve the situation with renormalizability. But of course, perhaps useful in very contexts, in various contexts, for example, in cosmology.
Thank you. But Orava gravity was proposed exactly because it's power counting renormalizable. And the last papers, basically, I would say that, I mean, there is people, I don't know if there is Yuri here, but basically there are papers already not completed, but they are almost shown that it's perturbatively renormalizable. It's very simple. The idea by Orava gravity is that you add these purely spatial derivatives, so you don't have the stochastic problem. You improve the convergence of the propagator. And the power counting renormalizability was the main motivation. Now, I'm not saying, look.
But as far as I remember, the realistic version was not proved to be renormalizable. Right?
Exactly that. The projectable one was proved, but as other problems.
Not realistic.
The one realistic one, they have basically almost completed the demonstration. There was a paper, it was very funny. When some time ago, there was a paper proving that there were no cancellation, that it was going wrong. And then Sibiriakov pointed out a mistake, and then all these divergences canceled away. And now they did the calculation, everything worked, and now they are basically looking at a beta function, but it looks like it's working. And okay, what you get out of this? Okay, is a quantum, in that case, it's a workable quantum theory gravity as UV violation, is CPT invariant, which is protecting some of the nastier terms for the constraints, but to me, and I close it, it's more interesting because there are a lot of features of this theory, like the calls in this theory, which are very surprisingly showing the resilience of all the thermodynamical aspects that I think are very instructive. Anyway, whatever is the reality about.
Well, but for evolution's gravity, yes, it is good, but it has only one disadvantage. That it seems to, in the most popular form, it cannot be reduced to usual Einstein-Hilbert limit. So we have to introduce intermediate terms with second special divergences. But perhaps in this case, the theory really is better.
There are two known phenomena. There is two branches, basically, of the theory that, for example, are giving the Collins on. One is so-called the phenomenological branch, which even low energy at the moment is not in disagreement with observation. So it's not excluded even the low energy part of the theory, although it is severely constrained. And so the basic mechanism, I just want to say that is the way you protect the point is that the gravity is difficult to constrain the Lorentz breaking for the moment, but matter is very well constrained. And the point is that the mechanism by which you percolate in the matter sector, if you don't start with Lorentz breaking the matter sector, you can percolate anyway by radiative correction. But the problem is that if the scale of Lorentz breaking in the gravity sector is below the Planck scale, given that the coupling is Newton, which is the Planck scale, if you like, then basically you get suppression, which are the mass of Lorentz breaking divided by the mass of Planck scale. And the mass of Lorentz breaking in the gravity sector of Orava has to be at least 10 to the 16 GeV, if not lower, for other reason, because you want for technical reason. And so in a sense, that is helping protecting the matter sector in Orava. So I'm not know if in the end it will work. I'm not saying advocating that this is the definitive. I'm just saying that the status at the time is that there is a phenomenological branch which is still past the current constraint.
Just a brief follow-up on that. If you look at the RG flow of Orava models, you see that what you would like to have is that the RG can restore the symmetry in the infrared, but it does not happen.
Mm-hmm. But that doesn't mean that is ruled out.
Well, it puts very strong constraints.
Yes. But they are not, it's not
No,
allowed.
of
There
course,
are
you can-
combination of the parameters that are still allowed. In the parameter
Sure.
space, you are still corners which are allowed.
Sure,
But
but it is unlikely.
It tells you that at infrared scales, the breaking has to be tiny because it's constrained that if you go up in energy, it has to be even tinier.
If you express the it's a technical problem, but if you express the action in terms of the shear, the acceleration, the twist of the ether field, you will see that basically you have a constraint on some of these that have to be zero, and other which are completely free. There are axes which are free. This is, for example, very well discussed in a recent paper by Ted Jacobson on rotating black hole in Einstein ether. Correct. But what I mean is that it's not worse than other situation of other modified theory from that point of view. So, and there is still the fact that it looks like it is, very normalizable. So that is a big pro, because at least you have one theory which is perturbatively renormalizable. I wouldn't throw it away just because there are in the parameter space, some of those have to be zero.
If I can make a question regarding the Jérôme Martin. A few years ago, I saw a talk by Jérôme Martin, and they were actually, if I understand it correctly, their aim was to find entanglement in the cosmic microwave radiation, so in the spectrum. My question is, if that is established and equivocally, if there is some sort of entanglement, and other groups, if I remember, either in Vienna, also in the United States, I don't know if Steinhardt and others were doing that. If that entanglement is found in the cosmic microwave, will that mean something for quantum of gravity, or is just some quantum thing for the cosmic microwave background? Will this mean something for the density perturbation? Because that's what was the provocative claim that they were putting.
Right, so again, I have not worked on this topic, but I think it would be a big problem for having thermal fluctuations as the origin of perturbations. So I think it's very important. So I don't know what you think.
I mean, I don't know how this works either.
Yeah, so they are on the archive. So.
There's also
But
there's
anyway,
another group.
to say something about quantum nature of gravity, you would first observe some gravitational waves and then study entanglement.
I'm a bit confused with all that because all the calculations of the CMB is completely classical.
Yeah.
So can you tell me this entanglement, how they're going to see it?
No, I cannot because I have
Okay.
not read.
So this is my question, is it completely
But
classical?
the answers and the answers are in these. So
Yeah, I just don't understand if somebody knew.
But when you generate cosmological, primordial perturbation, you do them in principle in a squeeze state. The point is that normally we don't think that the squeeze state is preserved, that there is a space.
That's what it's.
The problem is that, from what I understand, I'm not working in this field. There is a debate about the fact that this squeezing can be preserved and seen.
How they see it in the data, how they're going to see it in the data.
So anyway, there are these two groups that I know of. One of them is Japan. It's Sugumi Kano and Jiro Soda. They have a series of papers on that. Then the other one is Russell and Azor. But that's not my field. But again, references for you.
Yeah, thank you. But maybe if I can just rephrase the question and ask you for what Robert said was like, in principle, these gravitational waves can come from other sources which are not really, let me say inflation, something that happens in your universe. Maybe it could be cosmic strings, whatever they are.
Bouncy cosmology.
Right. But let's suppose to be that we understand that these waves, gravitational waves, comes from the expansion in their universe somehow, and we observe them. Would you say at least that this is an indirect?
Yeah, but you say, now you're asking a question in a way that I think is not valid, because if we just measure gravitational waves, how can we tell where they are?
I'm trying to make, let's say, the parallel with the scalar fluctuations. Of course, we don't observe
scalar fluctuations. We don't know that they are quantum origin.
What I'm saying is that, at least in the standard approach to really explain this CMB anisotropy, we imagine there is some like quantum seeds of these fluctuations.
That was not what Zergovich we're talking about.
But if you take standard approach,
what's the standard approach?
there is a computational relation for some scalar frequency.
No, so
Fluctuations.
in
You quantize those fluctuations.
If inflation is right, then it is true that the fluctuations are quantum
Okay. And that was my.
But they are.
But there's no
there are
proof.
the
There are no proof
But
that is
you
that.
see what you see, you cannot be sure where it's coming from.
Sure.
We don't know
Of course,
the
there was some
origin.
radio waves, we cannot say the electromagnetic waves are quantum. I agree with that. I'm just saying that. So your answer would be that it's not even an indirect test.
Not even an indirect.
I would be more confident and say that it's somehow an indirect.
But if you find entanglement in some way.
Sure, that would be
If you
a
have
direct. That one be a direct test.
Yeah, if you have other evidence telling you that inflation is the actual mechanism generating them, then inflation plus the detection of the gravitational waves fitting
Would be a proof of,
prediction,
yes.
then you can say, well, then the mechanism must be. But how much would tell you about quantum gravity?
I think it would be an indirect test.
I mean,
Not quantum
imagine
gravity.
we do an experiment and we prove that there are gravitons. Have we solved quantum gravity?
No, but that's what I'm
But
saying.
he
We
didn't
should
ask that. He
distinguish
said
between-
quantum origin, some kind of
Yeah,
quantum.
but basically you're saying quantum origin that is
Some-
coming
some
from the
hinting by-
quantization of gravitational perturbation.
No, I'm not saying that if you then explain, you see that there's some quantum nature of gravity, you are solving quantum gravity. But that's why I made the distinction between quantum gravity approaches and testing.
But what-
Exactly, we have a new question in the back.
You know, at least a comment. I wanted to make a brief comment on one tabletop paradigm this is related to. So this is the stimulated absorption of single gravitons, which we recently worked with the.
Maybe come closer, Srinath.
Yeah, we cannot hear you.
Yeah, but with the group of Gubitosi in Stockholm University. So I'm Stefano, I'm a postdoc here. So the work is where you look at gravitational waves in the LIGO band and see if you see stimulated absorption events just like radiative processes in electromagnetism. And why this is interesting is because previously this was thought infeasible. So if you look at the rate for an individual atom, so spontaneously emit a graviton, you will get something like it would take 10 to 40 seconds for the atom to spontaneously emit a graviton. So what we look at is instead of a single atom, you look at collective oscillations of an acoustic bar. So there were these Weber bars, some of you heard of previously in operation to detect classical gravitational waves, but they were measuring position of these bars. So we quantize this Matthew system and see what is the response of the system to an incoming gravitational wave and measure the energy of one of the acoustic modes of the bar. And the question that would be relevant there is what would you infer if you see a quantum jump happening in this one of these acoustic modes in response to a gravitational wave that is stimulating the system. And if you believe that linearized gravity is quantized how in the same way as an effective field theory, one has to deduce that the gravitational wave also lost a single quantum in the process. And by energy conservation, you can argue that just like in the photoelectric effect, this is one signature of it's a first clue for the quantum nature of gravity of gravitons. Yeah.
Sorry, you quantize the bar? Or
Yeah, so
the bar is normal.
So bar is let's say 15 kilogram bar is one system that we would optimize for the LIGO band frequencies. But then you can take this as a collection of many atoms, oscillating coupled atoms in an elastic model for the bar. And then you take the acoustic modes of that. So you can really quantize those acoustic modes. So you can go from individual atom picture to this collective modes of the bar. And there you see, you can see that this gives much improved cross sections and realistic time scales. For example, as opposed to an atom which cannot radiatively emit a graviton, you can show that the stimulated processes happens at a rate of 1 Hertz with the bar. And it's also not too surprising because these bars were initially were proposed to detect classical gravitational waves. So we get that massive enhancement. And
are you upcycling the old experiment with the old Weber bars?
So you would need, for example, 2 orders of magnitude improvements in the quality factor of the bars and the lowest temperatures that you need. Like you have to ground state cool the system and wait for single excitation in the bar to infer a single graviton exchange event.
And how realistic is to make such an experiment in the next, I don't know, 20 years?
Yeah, so I think it's so basically people have ground state cooled, like the LIGO mirror, which is 40 kilogram mass. They have cooled it down to something like 9 phonomes. So it's very low very low phonons in the system. So you can, in principle, go towards the ground state of massive mirrors, but this is the center of mass mode of the hydrometer. Here you are looking at acoustic modes and then the ground state for massive systems.
So how long do you think it will take to make an experiment?
Might maybe 5, 10, 5. I mean, in the sense it would. I mean, the sense that you have to ground state cooling is more or less possible. You can do with laser cooling or something. You also need to measure this energy, like quantized excitations occurring in the bar, or at a macroscopic level. That is the technological capability probably we do not have. But there are ways to transfuse this excitation to another smaller mode, and so it's a matter of probably looking at this experiment rather than, but then there is a lot you can benefit from the classical regime of the system because there are still Weber bars in operation.
Okay, thanks. Okay, another question there?
Yeah, I have a question about testing defined reality. So I heard that since given us certain modified theory of gravity and taking into account the solution for a compact star, so for a neutral star, the interior solution, the additional degrees of freedom of the modified classical theory will give an effective potential and a pressure for the neutral star solution that could be bigger than the one we have in general relativity, and this could trigger this process that happen at it's a particle physics process which is called Urca process, and then the neutral star, this bigger gravitational potential will trigger this process, which is not possible at a lower gravitational potential, and then this is an emission process which causes the neutron star to cooler faster than the expected in general relativity. So is this a promising way? Do you ever heard something about this? And the other is about gravitational waves. So that comes from some merger of black holes, or for example, so not necessarily primordial gravitational waves. There is any chance that the new gravitational degrees of freedom can leave an imprinting which has to satisfy the agreement, the constraint given by time, full sub-period, and so on, but that could still detect as additional polarization degrees, additional polarization of the gravitational waves with respect to the one of general relativity, or there would be some problem in the technology, in the precision to detect this additional polarization.
There are experiments, I mean, the LIGO thing, we try to see extra polarization. There is a problem to do it for transients, because, you can have up to 6 polarization modes.
What is a transient?
Transient is the measure, is something that comes and stays for a short time in your observer. Okay. So it's like measure of the effect. Okay. So you need a priori 6 kinds of interferometers with different orientation. Now we have 3 interferometers, CAGRED we take as well to before. The 2 LIGO have the same orientation, it doesn't work. So you could try to find the gravitational wave background, and then we have a way that we have proposed in order to look for extra polarizations, which has been used in the second, third, and now the fourth observing run. Up to now, there is no any kind of signature beyond the GR from the events that we have. But that's for the background, the stochastic gravitational wave background, which corresponds like the electromagnetic, you have the gravitational wave one. But for transient, which means all the data that we have up to now discovered after the collision of 2 compact objects, there are the instruments that we have and the orientation that we have is not optimal in order to look really for extra polarization.
Okay, thank you.
I think if you had extra polarization states in gravitational radiation, it would have an effect not just on the gravitational waves, but on the binary pulsars. And there are two binary pulsar measurements that are giving pretty accurate results. The Horst-Taylor one that's been observed for over 30 years now, and the double pulsar. And there's currently no evidence of any extra modes. So that sort of suggests that, well, they're small, very small. But you asked about neutron stars. When you're testing modified gravity, I mean, I'm not an expert. I know the work that I did on neutron stars, I used the TOB equation, and it was just to constrain the parameters
of the modified theory.
Yeah.
For neutron stars, we have done some kind of constraints if you have kind of modified gravity, because you are going to have, for instance, if you have a scalar field, you are going to have scalar modes as well. Yeah. And what that is going to do is going to change the waveform. So we have put constraints from the first BNS kind of LIGO data we had. We put constraints in cases that you have axion fields, for instance, in the center of neutron stars. So you can put constraints. But we don't have up to now many binary neutron stars.
Nice. Yes, so I want to ask a question to the panelists. So do you think there is a single experiment that can, where if you find the deviation, you can certainly say that it has a quantum gravity origin, or in order to constrain quantum gravity, we need essentially a theory to tell us that there are deviations in multiple aspects, so on potentially detectable in multiple experiments, and we need to find a consistent deviation in all of them in order to really learn about quantum gravity.
So again, so your question.
So my point is say that I mean, I take we already commented on the gravitational waves. Okay, we say okay, if you find a deviation from the waveform that we expect from GR, it is not obvious that this quantum gravity could be a classical modification. Something similar could happen for Lorentz violation. If you find a violation, you cannot really say it is quantum gravity. So do you think there is a single experiment where if you find a deviation, you can say it is quantum gravity?
But I think that you know, I mean,
aside from tabletop, where the scope is really to say yes or no in terms of whether the nature of gravity is quantum.
Quantum and not modified gravity.
Yeah, I would say tabletop says whether gravity is quantum. It's about
quantum test of quantum physics.
Exactly, really quantum gravity.
But do you mean an experiment that you can
gravitational
do,
waves
that you can do, or you can
something.
Mentally do? Because
no, mentally do
no. Something that would be
really
doable in the
yes, I mean
lives.
gravitational waves and
in our lives, let's say, more or less.
Not necessarily in our lives, but an observation that people are testing or plan to do, where if we find a deviation from what we expect, we can really say it is quantum gravity.
And not modified gravity.
And not modified gravity.
Because if you don't say that we can do just creation of gravitons, but this we can
No, I mean something that is a lot low energy, sufficiently low energy.
That we can do in, let's say, maximum 30 years.
I mean, not at the Planck scale.
Imagine you do experiments that prove that there is no initial singularity, that there is a bounce. Then I don't know, I mean, I'm a classical. Well, you know, you can
modified gravity.
No, you can do, even an F of R can do that in principle.
Exactly.
But then you know what? There are two things that I know that no classical theory of gravity can change. One is signature and the other one is topology. So if you find, for example, that the topology of the universe, and this in principle was searched even in circle in the sky with a CMB. Imagine you find that the fundamental cell of our universe is not simply connected. So you have this circle in the sky, then I would say that the start must have been, there must be a sum over topology, you know, some kind of Euclidean path integral where you sum also topology and you select. Moreover, you know, the fact that you select a non-simply connected topology, for three-dimensional space, there are 18 topologies you can do, only one is simply connected. And if you find one non-simply connected, there must be a selection mechanism why it weights more in the path integral. So it would be a strong hint that something is going on, and you would give dynamics evidently at the Big Bang to something that normally is non-dynamic.
No, that is true.
But now here my question is how you are going to do this experiment, because that was done, for instance, that was studied a lot in the context of the CMB.
And they didn't find it.
Yes, but I'm not sure that they could ever find it, because to analyze the data of the CMB, they consider classical geometry. They consider GR with the famous lambda CDM. So by analyzing the raw data within a particular model, I'm not sure they could even find if there is a topology change. So a priori, yes, but in principle, I'm not sure that this would work either.
That is actually
Yeah, they put a bias from the beginning. They put something and they found what they put. So how they could find something outside the context within which they analyze their data.
So prior
So we're
really
condemned
problem
by
in
that.
testing the quantum gravity models.
The River-Robertson Walker is compatible with non-simply connected topologies. It doesn't tell you that it's R times R3. It could be times R3 over a deck group, so it's non-simply connected. So, but you say it's more. They were really assuming a GR plus lambda CDM.
That's how they analyze the data. Yeah. So that's why I think it's
then let's say that is an objection to what we have seen so far. So in principle, what you're saying is that it would be worth to redo the experiment in a proper the analysis of the data in a proper way, less bias, because I mean we have to agree before if this would be a signal of quantum gravity, because to me anything that is telling you that the topology is non-trivial, it means that there's somewhere there has been a topology change, because you don't have a reason to select one of the 17 not simply connected topology a priori. Of course, you can put it as an initial condition of the universe.
Although, I mean, I guess that is your built-in topology of the...
But that's not, you don't find, doesn't...
Topologies, then this will be Planck suppressed, since it's a quantum gravity effect. And so not
exactly, it could happen, and people would expect that this can happen only. Imagine you have a regularization of the Big Bang, and there is quantum gravity regime. There, maybe every time you have this bounce, you do your set you have to see what topology are dominating, and there is not an argument that tells you that the simply connected one is dominating. I was telling that before. This was part of the argument by Hawking in 2004, tried to argument that only global hyperbolic space-time could
but my question was how this can probe quantum gravity. So if this is a quantum gravity effect, don't you think this would be Planck suppressed and so not accessible by experiments?
No, because once you've changed the topology, you see that the fundamental cell, you see these multiple impulses. It's not that you are seeing the change, you're seeing the effect of it, but you see that the topology is not simply connected. See, normally we think,
but
you take a River-Robertson Walker.
Can it be not simply connected also classically?
I think that we're not understanding each other. Of course, I'm not saying that. The problem is that there is no mechanism, classically or semi-classically, that can describe the topology change. You know that in quantum filtering space-time, if you try to change the topology, you have a paroxystic particle creation. There is a kind of censorship to that. The only way you can change topology is by having a quantum gravity.
So do you think this will be Planck suppressed?
But once it happens, it happens. So there must be a selection rule. That what I'm trying to say is that if something that we don't consider dynamical in classical or in classical theory, we find out that at some point, the objection is what we just said with Alessia. You can say, okay, for some reason, out of 18 special non-simply connected topology, 17 non-simply connected topology of the universe that can be compatible with River-Robertson Walker, we end up in one, there is no change. It was given by God from the start. That is my answer to that. Then, okay, but normally you would expect that if there is 1/17, there must be some selection mechanism, no? Because how do you prefer one over the other? It's a bit like the mechanism you were saying. One 3 dimensions are macroscopic and the other one are not. This was providing a quantum gravitational mechanism based on basically intertwining string theory. It is an explanation to explain why we see a world which has only 3 large spatial dimensions. I would say that similarly, you will be induced to say that most probably it is a sign of quantum gravity if you don't decide to be content with the fact that this is an initial condition.
Let me just address your question. What, with another question, what if you detect a new particle, and that new particle decays, and in that decaying process, you are forced to accept that there is somewhere there a spin 2 particle, a gravity, energy, you need it. Is that an increase, a small function of a gravity?
Spin 2 tells me that there is quantum gravity, not which quantum
then
gravity.
you answer my question. So that's it. You produce it, you find it, and in the process of analyzing it, you need a spin 2 particle. So there is the gravity. And that's quantum gravity.
Yes, but which quantum gravity?
And she was asking about like whether we can.
I would say the area gravity in any theory.
I hope so.
Because there is people thinking that there are no gravitons. No, there is.
I mean, there is emergent gravity. There is.
So your question is not only quantum gravity, which quantum gravity? Then I think.
No, I mean, that is, I probably to say like which quantum gravity, what we need is a theory that tells, or some theories telling us in gravitational waves, you get this modification. In CMB, you get this modification. In this other thing, you get this modification, and then you consistently find those modifications, and then it is much more constraining. But even then, you could look up maybe another.
That you need like watching a painter and then you go X-ray.
No, I mean, yeah, it's really unlikely.
It's very unlikely.
Yes, it's yeah, but I didn't want to bring this pessimistic view, but I thought it was an important point.
I'll be satisfied with funding a can make some power.
There was a
just a small comment. So if the goal is to distinguish between different approaches, there is something that comes up with the loop quantum gravity, that is the discreteness of the spectrum of area, volume, angles, and so on. So if you can verify, if you have some effects, the answer probably will not be able to measure this directly. If you can relate the effects that you measure directly to the discreteness of these quantities, and in particular, for instance, also check the value of gamma of the Berberine parameter. So this would be something that hints very strongly towards.
But it's going to be.
No, in the sense that if you have gamma, or if you have another theory that has another parameter, you are only putting constraints on the parameters.
Can I add something to this? Can I add something quick to this discussion? Because I think I go back to what I said at the beginning of the small comments I make. What is important for quantum gravity is to explain the universe in which we live. So even though even myself, I worked for some time in loop quantum gravity or cosmology, what I find as an issue that needs desperately to be addressed there is apart the kind of Lorentzian signature that is an important thing, is as well the matter part. So the matter Hamiltonian there is put by hand. So before we go to see how such a theory could be confirmed from the data, it is important, if we want to explain the universe in which we live, not to take the matter part, we put it by hand, because a theory that explains everything would as well have the metric, the geometry, but as well the matter part, which we don't do. So that's a comment before we run to that.
I mean, in some approaches, there is progress in that direction. I mean, if
the majority of the studies that have been done, you just take the matter Hamiltonian standard theory, you put it by hand, and then you see how it's going to be changed with the dynamics which are modified.
Every theory has its own. Every theory has its own constraints. Okay, I don't want to speak about how this is constrained in other theories, but for instance, in asymptotic safety, the idea is that if you couple gravity with matter, the two combined must be ultraviolet complete, and then you can roll out matter models in this way. So, for instance, you see that the standard model is compatible with.
Don't say that, but I'm saying that's a very important thing. And as far as I know, the majority of the studies, not all in the LQC, the matter part is put by hand. That's all I said. So the important thing to have the matter, I was thinking about that. And the other thing which I said is important is about the signature. So before we are able to address these very important questions with respect to where we live, there is time before we jump how we can separate which correct theory, which is the correct theory.
I have a reaction to this because, of course, when we address the problem of quantum gravity, there are two different ways to go there. One is the theory of everything, in which you have quantum gravity that appears together with some more fundamental than the standard model theory. And another way to approach quantum gravity is to say, I want to study the quantum aspects of gravity. So you separate the problem. On one hand, you have matter, and you focus on a very specific problem that is the quantum properties of the gravitational field. So I understand the disappointment of having to couple matter. So, and by the way, the fact that you can couple standard matter with your quantum gravity theory, to me, is already a very nice achievement. But I don't see the necessity to jump to a theory that has everything, even though I share with you some passion for non-commutative geometry that is compatible with the quantum gravity. Actually, non-commutative geometry needs something that brings the non-commutativity, the quantum discreteness that can come from
non-commutativity. But non-commutativity is also, it also exists in quantum mechanics, something very fundamental.
Well, but in non-commutative geometry, you need it in the background.
You need the background. But what I find, and if I had something better to propose, it had been proposed long ago, but we should not forget that when we try to find all these ways to test quantum gravity in the context of the LQC, the matter Hamiltonian is put by hand. So if you had in mind, for instance, the CMB experiment or God knows what, I think before we do that, we have to see how this matter part emerges. Otherwise, I don't think that the constraint that we can find has any value in order to test the LQG motivated model. That's all I try to say. If people, what they do, they take, for instance, a scalar field with a given potential, say how the dynamics of this hypothetical inflationary model would be in the context of LQC. So I take modified Friedman equation and I put the Mairi-Platon field with, to me, this case, I'm sorry to be very, now we're recorded, but I don't mind. This, I don't think that has any scientific value. It's just a kind of calculation we can do, we do it, but we don't learn anything.
Before we are at 4:33, so we can go on, but in principle we have exhausted our time. So you are the czar of the. So you tell me, I am just here. I think she has to save like a collaboration
Then.
So if you like, who wants to remain
at the barbecue, we'll keep discussing.
Maybe last question.
If who wants to remain, can remain, and we can keep discussing, and who wants to go, I can go. Right?
You maybe allow me to give like one comment, 1 minute. Okay. I agree. I mean, in general, even before going into experiment, we should make sure that our theories are fully internally consistent, which also includes matter. Maybe we can postpone if, it is one person to study all of the unitarity properties and everything that makes the theory fully internally consistent, also with matter. And this is already highly constraining. This is something that we learned actually in the past 2 weeks. Still, a theory that is fully consistent is not obvious that describes our universe. So then it comes to the connection with observations, and also in relation to one of your first comments, if we have a theory that is consistent and normalizable, but doesn't connect with our universe, what do we do? A theory that is normalizable or consistent from every other viewpoint doesn't then necessarily describe our universe. Then there is the second test of yes, we can have multiple theories that are fully consistent, and then only one of them at best describes our universe. But regarding the last point, so one thing that has been discussed in the past 2 weeks of workshop where we discussed the formal aspects. After some effort and after some heated discussion, there is a kind of an agreement that at least at low energies, one should reproduce effective field theories. And then one important job of each quantum gravity theory is to restrict the parameters. You cannot have everything for each parameter. You need like a finite number of pre-parameters, and the rest you should pinpoint exactly at least the range of variation for many of them. And then this range of variation have to be compatible with unitarity, and all of that comes from effective field theory, but also with the experiments. So this would be the connection also with the past discussions. So see.
I'm tempted to do a remark, but I will not do it. For the sake of closing the discussion, but I'm happy to do it late because after the discussion, it kind of nihilist point of view that, but you wanted to say something.
I just wanted to thank all of you.
Okay.